pleasure to welcome, if you can call it that, Qiaomin Qi. She's been here since 2019, but off and on for the last several years. Got her PhD at the University of Illinois at Urbana-Champaign under the tutelage of Yi Lu. Then did a postdoc with David Rachel at MIT, and joined us as a visiting assistant professor in 2019, and has been teaching a broad range of courses. Our talk today is about power of Monte Carlo Methods, Tree Search, Convergence and Stability. So, welcome, Qiaomin. Look forward to your talk.
Thank you, Mark, for the nice introduction. It's my great pleasure to speak here. Today, I will talk about my recent work on understanding and applying Monte Carlo methods in reinforcement learning. Please feel free to interrupt me if you have any questions during the talk. Let me start with motivating applications. One critical societal infrastructure is the data networks, which transform our life in many ways, including how we do business, entertainment, and even maintain social network. For example, today's data centers power many services and applications. And having access to these services becomes an important part of our daily life and work. Data center consists of many servers and also a large storage system for maintaining a massive amount of data, and a large network for data exchange both within and outside the data centers. And these applications share the underlying resources here. A fundamental problem is how to allocate resources for different applications, and also different jobs from the same application. For example, when you typed a query on Amazon, the query will send to one of the data center. And the system needs to decide which server to process your request. Then they can return the results as quick as possible. And imagine that many other queries sent to the data center almost at the same time. And how to schedule this request across the servers is important for providing high quality service. So efficient utilization of the resources here has the huge impact on customer satisfaction, and of course, as the company's revenue. Resource allocation is common and a critical problem, not just in data center, but also in many other applications, including transportation network, healthcare, inventory control, and so on. And in all these applications, we want to design practical algorithms and also provide rigorous characterization of the performance in terms of throughput, delay, revenue, etc. And driven by these applications, my research involves two different but complementary approaches here, the model-driven approach and the data-driven approach. Now, let me first explain what these two approaches are. For the model-driven approach, the typical design flow is follows. We start with accurate modeling of the system, such as queuing networks, and then based on our intuition or domain knowledge to design an algorithm. And we might run simulations to test and maybe tune the algorithm for better performance. And then we moved on to the performance guarantee. Most existing research on resource allocation problems are mainly based on model-driven approach, and there has been a rich literature on this line of work. And actually, many audience here have important contribution to this line. And it has significantly deepened our understanding of scheduling theory and also for the system management. On the other hand, it is also well recognized that there are many challenges here. First, the underlying system may be too complicated, and we don't have accurate mathematical model. And secondary, sometimes even we have the accurate model, optimal policies may be difficult to find. And this is true even for some simple models. These issues are very challenging. However, these days, there are new opportunities of addressing them by taking advantage of the availability of fine-grained data sets that records the system's behavior. Data-driven approach, particularly reinforcement learning, has the potential of addressing the challenges here. It can learn the system dynamics from the data, and it can also discover new policies by interacting with the system. As I mentioned, my research spans both approaches here. In particular, one line of my work mainly focused on the model-driven approach for resource allocation problem, using tools from stochastic networks, queuing theory, and applied probability for performance modeling and analysis. And in the context of data center, I have worked on various resource allocation problems, including load balancing, scheduling in the computing cluster, and other resource allocation problems. And many resource allocation problems here manifest as online decision-making problems. Recently, my work explored data-driven approach using reinforcement learning and the statistical analysis. My work mainly focused on addressing the challenges of decision-making in complex systems. And I have worked on both the non-parametric and the parametric method and Monte Carlo method, which I'm going to talk about today. And from the single agent learning agents to multi-agent systems. And I also explored the reinforcement learning for network controls, for network and queuing control. Today, I will mainly focus on my work on reinforcement learning. We know recently, reinforcement learning have achieved a remarkable empirical success in applications like games and robotics. It has also shown promising performance in other areas as well. However, it's also well recognized that the existing reinforcement learning techniques are insufficient in dealing with many of the complexities that arise in real-world problems. These include large staged action space and maybe time-varying environments, and sometimes involve multiple strategic agents. These issues are very common in many applications that I mentioned. And they have motivated me to develop the new reinforcement learning techniques for addressing these issues. And the goal here is to build a solid foundation of reinforcement learning for real-world applications. In today's talk, I will mainly focus on one line of my work that studies the Monte Carlo methods for problems with large and even unbounded state space. And I will also talk about how to achieve stability in these problems. This talk is mainly based on the following several papers with my excellent collaborators. Let me start with the formulation for reinforcement learning, which is the Markov decision process. In an MDP, an agent, or typically decision maker, interacts with the environment as follows. At each time step, the agent will observe the state of the environment and take an action, and then to receive some reward as feedback. And the environment then make a transitions to a new state. And the interaction repeats and continues. A policy of the agents map each stage to a distribution of actions. Basically, it specifies the probability of playing a particular action given the current state. And the goal of the agents is to find a policy that maximizes the total discounted reward. Here, gamma is the discounted factor between 0 and 1. When the model is unknown, it becomes the reinforcement learning problem. Now, the agents want to learn a good policy through the interaction with the environment. And the data can be either from real experience or maybe it comes from simulated data.
Qiaomin, I have a question.
Yeah.
Sorry, this is my face again. This is Mark. Given the example that you provided earlier, I'm just a little surprised to see that we're still looking at a discounted problem. Is there a reason why we choose a discounted problem as opposed to an average problem? I don't even know how to choose a discount rate in the cases where we have things happening so quickly.
That's an excellent point. Indeed, in the first part of my talk, I mainly focused on the discounted case. And in the second part for the Q network control, I will also talk about average cost as well.
Great, thank you.
Yeah. Okay, so a couple of definitions that will be very helpful here. So in an MDP, we know the staged action value function, also called Q function, can be defined in two different ways. For a fixed policy pi and a staged action pair, the original definition of the Q function is the expected total reward starting from this particular state and with this particular action A at the first step, which might deviate from the policy pi, but then follow policy pi for all subsequent actions. So by this definition here, one can simulate the one or multiple trajectories under the policy pi and use the total empirical return as an estimate for the corresponding Q value. And we also know the Q function satisfies the so-called Bellman fixed points equation. So say we have an estimate Q value, Q function, Q old here. Now, given a single steps transition from the staged action SA, we can update our estimates for the Q value as the sum of the immediate reward and also the old estimate Q value of the next staged action pair. So here we bootstrapped from an existing old estimate, and it serves as an estimate of the remaining term in the summation here. These two ideas, to me, I think they are basis of many value-based reinforcement learning methods. And actually many algorithms, they used a combination of these two ideas. In this talk, I mainly focused on Monte Carlo method. It has the significant simulation components. So it's closest to the first extreme here. And one example would be multi-steps look ahead. So compared with the bootstrapping here, then instead of one step to look ahead, we might run multi-step to look ahead. Many well-known reinforcement learning methods are primarily based on Bellman equation, including value iteration, like TD learning, Q learning, or like also fitted value iteration. They're very popular and have been extensively studied. Here focused on understanding Monte Carlo method, which is also very powerful. So MC method take advantage of simulators, which can be available for many applications. And in some domain, we might have abundant real-world data that can be utilized to build an approximates the simulation model. And as we have sourced in the previous slide, here by using Monte Carlo method, we can just focus on the value of policy locally at a single state. That's what we are particularly interested in. So we don't really need to solve the entire MDP. And the complexity here won't scale through the state space. And a result here is we can do decision time planning, meaning we can learning or do planning only for the states that we encountered. So it's also more robust when the environment is not truly Markovian. But in contrast, the Bellman equation relies on the Markovian assumption. applications that can benefit from Monte Carlo method, including games like Go and video games. And as I mentioned, applications that I'm particularly interested in is the resource allocation. And usually it's easy to simulate either from artificial simulator or maybe synthetic simulator built from real world data. And typically problems here involve large and even unbounded state space. So the local property of the MC method make it a very great fit for or for learning a decision when we encounter a new state in real time. And sometimes the system might not truly Markovian, so let's make Monte Carlo methods also effective sometimes. With this background in mind, today I will talk about two of my work related to MC method. I will first focus on Monte Carlo Tree Search, and then I will talk about the data-driven queuing network control. So let's start with MCTS. We know Monte Carlo Tree Search is a search framework for finding optimal actions. And there are many variants of MCTS. Today, we'll focus on the most popular one in the family called Upper Confidence Bound-for Tree, or UCT. It has been used in many applications. The most famous one you might have heard about is AlphaGo 0. That's Beast Human Champion. However, despite of its popularity, its performance guarantee is not clear. Today, I will focus on a principled analysis of MCTS. Here, we assumed access to a simulator so we can sample trajectories. And the goal here is to find a good action for a single state. That's maybe a critical state or maybe a state we are particularly interested. Later, we will see how we can generalize to the full state space by using supervised learning. But just for now, that's focused on learning for a single agent. MCTS takes the query state as the input and outputs the recommendation for action. At a high level, MCTS combines several ingredients: simulation, multi-step look-ahead, and the smart sampling. More specifically, by simulation, I mean we will imagine what might happen starting from the query state in a short-term future, and simulate the multiple trajectories starting from the query state as. And moreover, we will learn adaptively from all this imaginary experience, so we can allocate the future simulation towards the more promising trajectories. I think the most important ingredients here is adapt sampling. It is the one makes the MCTS more powerful than naive the Monte Carlo method, but of course also make the analysis challenging, as we will see later. Now, let's look into a little bit more details of MCTS here. For simplicity, assume there are only two actions, A1 and A2 here, and all the transition is deterministic. And we can actually easily generalize all the algorithm analysis to a stochastic setting. The tree here represents all possible trajectories of the MDP, starting from the query state as up to H steps. And here is an example with up to 4 steps starting from the query state. And each node on the tree represents a state. So the root node is the query state. And each edge corresponding to an action. So from the query state as, action A1 leads to state S1, and action A2 leads to state X2, and so on. And this is just an imaginary tree. In practice, the MCTS will build the tree gradually from states and actions encountered during the simulation. Starting from the loose node, we'll run multiple simulation or trajectories up to edge steps, and always starting from the query state. Say the first simulation is on least path. So it's just a sequence of staged action, reward, the next stage, the next action, next reward, etc. And up to some leaf node.
Qiaomin? Sorry, I'm curious. It looks like you're looking at a situation where you have deterministic dynamics. I take an action and then the next state is determined.
Yes.
Is that what you're doing?
Yeah, so just for simplicity in the talk, I will use deterministic transition for illustration, but the algorithm and analysis can actually be extended to the stochastic setting.
Thank you.
Yeah. Okay, if no more question, let me continue. So say the first simulation is on this trajectory here. And when we reach a leaf node, say if we have an access to an old estimate of the value function, then maybe we can use it as an estimate for the future reward starting from the leaf node. But if we don't, it doesn't matter. We can simply assign the value 0 as an estimate for the leaf node here. Now, for each staged action pair on the trajectory here, we'll keep an estimate Q value using the return of the trajectory. So this is just one sample path. And maybe the second simulation is on this trajectory. And similarly, we'll perform the updates for the Q value for the staged action pair on the path. And say we might have the other simulation, say the blue one here, and similarly perform the update. And say we finish it n simulation. So in total, we have the n trajectories here. And then at the end, we'll output the estimated Q value for the loose node or the query state. And now with the estimated Q value, then we can obtain an action. So it can be greedy with respect to the Q value estimates, or it can be maybe softmax by using the so-called Boltzmann policy with respect to the estimate Q value, and also with incorporating a temperature parameter tau. So then we can take an action according to either greedy or the softmax policy. So this is the overall framework of MCTS. But wait, one thing I haven't told you is how we choose these trajectories for simulation. Or maybe more specifically, whenever we reach a node on the tree, which action or which edge should we choose at each node during a simulation? And the policy that determines the action here is corresponding to the so-called tree policy. And a very simple policy is just to choose the action uniformly randomly. This corresponding to the so-called sparse sampling that started earlier. And previously, I mentioned that MCTS doing something adaptive. The key idea here is to view the decision-making at each node as a multi-unbanded problem. So then we can borrow ideas from the bandit literature. In particular, now to choose an action, we can use the classical bandit algorithm called upper confidence bound. And recall that for each staged action pair or each edge on the tree, we maintain an estimated Q value. And according to UCB, we will choose an action that maximizes the sum of the empirical value and a bonus term. And typically, the bonus term here encourages exploration for actions that have not been visited often yet. And we know in MAB, the standard choice for the bonus term is logarithmic in t. Here, t corresponding to the total number of visits for this node so far. And this particular bonus term comes from the Hofding concentration inequality for RID reward sequence. However, it turns out that for MCTS with a tree structure, we need to use a bonus term that is the polynomials in T. This is actually very crucial. I will come back to these points later. Now, just say we used such polynomial bonus term for the balancing the exploration and exploitation. Then we can establish the following guarantee for MCTS. Suppose that at each simulation, we use an old estimate that we had old for the leaf node estimate, which is epsilon accurate. And say we run n simulations and each up to h steps. And then we output the estimate Q values for the loose node. And the theorem say the error bound for the loose node or the query state has two parts. The first part is due to the error of the leaf node. And the second part comes from finite simulation. So if the number of simulations n is large enough, then the first terms will dominate. And recall that here, gamma is the discounted factor between 0 and 1. So we can ensure that this term is always smaller than the accuracy level of the old estimates. So in some sense, the MCTS improved the estimates for the loose node here over the old estimate. And the result...
Could you remind us what is H?
H is the number of steps you run the simulation, or you can think about is the depth of the tree for the MCTS.
Okay, thank you.
Yeah. Okay. So sometimes we might not have an estimate for the loose node, and then we maybe just simply plug in the value 0. And the results say, even if this is the case, if the reward is bounded, then we have a trivial upper bound for the leaf node estimate as here. So the results we get here is still meaningful. And here I want to answer the questions that Mark asked before about why we consider this discounted case. So far, we are only able to rigorously establish the convergence guarantee for the discounted case. And for the average cost setting, so we believe it can also be established with a similar guarantee, but with extra condition in terms of the algorithmicity assumption. So meaning we need the Markov chain to have similar behavior and kind of like have a construction behavior. And that's typically assumed in the average cost. But so far, this is what we have, but we believe this can be done also for average cost.
So could I ask another question? When you have a problem like Go, where the reward really comes from winning the game at the very end of quite a deep search, it feels to me like just applying this approximation of 0 a few layers into the tree is not looking far enough so that you actually ever get to the end of the game. So how would you get learning in that context?
That's an excellent question. So indeed, for games where the reward only comes to the very end, so then directly plugging a value 0 might not be so efficient. Then indeed, we need some kind of like estimates for the leaf node. A simple approach people would typically try is kind of like use the random rollout. You maybe just try until you reach the end of this game. You don't really care about the policy you used for the estimates. So we just provide some estimates for the leaf node. And the other thing here is for such problems, And typically, instead of, so here I mainly focused on learning for a single state. And as we will see next, and sometimes you might want to maintain an estimate from all your previous historical data. So in this way, you can also build an estimate for the leaf node as well.
Got it. Thank you.
Qiaomin.
Jim,
Yeah, a question here. Your results here, ST. What's small t?
Oh, sorry. There should be a typo here. Here S should be the query state or the loose node.
I see. So you're really looking at the query state or the root of your sort of imaginary tree.
Yes.
You didn't claim any result on these leaves at the leaf node, right? So there's no this result here, statement here. There's nothing says about leaf node, how good these queues are. I'm right?
Yes. So indeed, for the results here, we have the guarantee for the loose node, but through the proof, we can actually also establish some similar guarantee, but with different upper bound here for the node on the intermediate, for the states on the intermediate node on the tree as well.
Okay, so just maybe one more step clarification, just simple clarification. So this N is this N simulation here, N replication is just all starting from that root node.
Yeah,
right?
or starting from the query state or the loose node.
Okay. I see.
Yeah.
So if you really want to care about the quality of these leaf nodes estimation, then in the future, whatever you need, maybe a lot more samples, a lot of simulation starting from each of these leaf nodes, right? I'm right? That's a likely path.
Yes.
Okay. Thank you.
Sorry, Qiaomin, since you mentioned the average case, I have to ask. I'm just unclear. What would be, or what do you conjecture would be? Maybe I missed it. The replacement.
The discounted.
No. Yeah. What replaces the discounted reward here in the average case? What would be the if part of this, if that holds?
So
right? Where your cursor is now.
It's not so clear at the top of my head at this moment, but I believed it's related to some kind of like a missing behavior of the Markov chain for average cost case.
I'm just wondering do you have a hypothesis here or a requirement here that V old be within epsilon of V star at S? And I just don't know what might replace that.
So I think the key difference here will be the discounted factor. So I don't think we have the gamma 3 power of H anymore, but will be some other constants that's smaller than 1, that depending on the mixing behavior of the Markov chain.
Okay, let's move on. Okay, thank you.
Yeah.
I had a question, Qiaomin. That constant on the 1 over square root n there, how do the number of leaf nodes play a role? I would have thought that your samples need to get split across those leaf nodes, and then that should, can you say something about that? Yeah,
an excellent question. So that's why I don't put it here, right? No, so for a short answer here, it can depend on the number of leaf node, which means it can have exponential dependence on the depth H. And that's the worst case. And in general, if indeed the problem is very hard, so it will be a hard instance, you can imagine this, it will be finding a needle in a haystack. And there's no much you can do. So you always experience such the worst case dependence. But in some case, for sometimes the problem is the kind of like easier instance, then the dependence here can be better. So it's not really have this exponential dependence up to the exponential of H.
Thanks.
If no more question, let me move on. I don't think I have much time to cover into the details to the proof. So I just want to mention here, previously I mentioned why the classical logarithmic in T, in general, is not guaranteed to work. And the main reason here is when you look at the MAB upper level of the tree, the reward at each action or reward at the reward sequence is no longer IID. This coming from the adaptive sampling of the procedure within MCTS. So this is exactly why, in general, logarithmic bonus term is not guaranteed to work. But if we used a polynomial bonus term, then we can show the reward sequence concentrate along its limiting value, and the tail bound has done a polynomial term like this. And an interesting fact here is AlphaGo 0 also use similar polynomial bonus term for their work. And we can also generalize all analysis and algorithm to a two-player zero-sum games. Next, let me briefly discuss some extension of the results I talked about here. So far, we have shown that for a single query state, we can use the MCTS to learn a good estimate for the Q value. And say we can do this for finite many states, say M states. Now, the question here is, can we generalize the estimates to other unseen state when the problem has the large or even continuous state space? And indeed, we can do this by formulating as the regression problem. So we want to predict the Q value for a state. And we are given M training data, and state SI is the feature, and the Q value becomes the label. And now you can use your favorite supervised learning algorithm and the function approximation. AlphaGo 0 use deep neural network, and you can also use the non-parametric approach like nearest neighbor. And moreover, we can do this iteratively. So MCTS will generate high quality training data, and then supervised learning will generalize this estimation to the entire state space. And then we can use the outputs of supervised learning as the leaf node estimate for the MCTS, which will further guide the MCTS to generate the new and improved training data and so on. So far, the results I talk about assumes the finite action space. Recently, we also generalized MCTS to continual action space setting. Now you can imagine each node on a tree becomes a continuous unbanded problem. Here we combine the MCTS with adaptive quantization of the action space. And again, using polynomial confidence bound is crucial, and we can obtain similar convergence guarantee here. We also evaluate our approach on several benchmarks from OpenAI Gym. So you can see our results here either match or improved over existing tree search method. In particular, for the lunar landing problem, our algorithm achieves the much better performance. So this is what I want to talk about for the MCTS part. I will pause here in case you have any questions. If not, I will continue. So for the second part, I will talk about reinforcement learning for queuing network control. Here is the simple queuing example for the scheduling problem. We have a single server and two buffers. And the jobs arrives to the buffers to be processed by the server. And typically, these buffers are modeled as infinite size. Say the server can only serve the one job at a time. Now, the system state can be described by the vector of the queue length. So you can see the state space becomes unbounded. In the language of MDP or reinforcement learning, the action here is the scheduling decision of the server about which queues to serve. And the goal here is to minimize the average total queue length, or equivalently, we try to minimize the delay for the incoming jobs. The queuing level can be more complicated for other problems. There may be multiple servers in parallel, and there may be also some constraint on which queues can be served simultaneously, like switch scheduling, or sometimes it becomes the routing problem for the incoming traffic to servers. Here we are interested in learning optimal policy purely from data without knowing the system dynamics. And reinforcement learning is the suitable framework for this learning task. Of course, using reinforcement learning has its own challenges here. Recall that a key characteristic is the unbounded state space. So traditional offline training and the deployed approach might not always work. Say for simplicity, the blue region here represents all the states we visited during the training phase. And in the real system, we might reach some states not included in the training, say a yellow state here, which can be far away from the training data. So the previously trained policy might not behave well here. For instance, they might keep serving an empty queue while the other queue is wrong. So decision time planning is necessary here, meaning we want the algorithm to have the ability to learn a good decision whenever a new state or new scenario is encountered. Previously, I mentioned as finding the optimal policy for minimizing the queue length typically is challenging. And even keeping the queue length finite is highly non-trivial. So we will first focus on the simpler problem of maintaining the queue length finite, which equivalently means we try to stabilize the system. You can also view stability as the necessary first step towards the optimality. And the notion of stability, we consider here the appropriate for reinforcement learning. Particularly, we call a policy sequence stable if the underlying system satisfies two conditions. First is boundedness, which basically means the most of the time, the system will stay in a bounded region. The second one is recurrence, which means if occasionally the system visits some states outside the bounded region, but it has the ability to recover from such undesirable states and then returns to this bounded region within the finite time step. And the questions that we are interested here is how can we learn a stable policy purely from data? And the idea is to use the Monte Carlo search method. So the overall algorithm works as follows. At each time step, starting from the initial stage, at each time step, this will query an MC oracle for the current state, and then gets the distribution of actions. You can view the distribution as the recommended or policy for the query state. And then we can take an action according to the recommendation distribution. And the system makes transitions to the next stage. And then we can repeat this process. So ideally, we hope that the outputs from the MC oracle are close to the optimal policy in some sense. Then if the system is stable under the optimal policy, then we might be able to claim stability of the approximate policy. And moreover, we hope that for each query, the oracle can compute and approximate the policy by only using finite samples. There are a couple of traits for MC oracles here. One is sparse sampling I mentioned earlier, and the other one is MCTS. So recall that for MCTS with proper parameters, the estimate Q value for the query states can be close to the optimal Q value with high probability. Now, if we construct a softmax policy from the estimated Q value, then we can upper bound the distance between the optimal policy and the induced softmax policy. So for in particular, the upper bound here can be very arbitrarily small, as long as we have a small error bound for the Q function and choose the temperature for the softmax properly. And of course, the natural question here is how small the error bound should be in order to achieve stability. And what's the sample complexity per time step? To answer these questions, we need to introduce the assumption here. In order to have hope for stability, the optimal policy itself should be stable, which means the optimal policy leads to a positive recurrent Markov chain. And it's also well known that the positive recurrence is equivalent to the existence of the so-called diagonal function. So this motivates us to assume that the Markov chain under the optimal policy satisfies a diagonal drift condition. So I'm going to skip the details here. Basically just assumes that the Markov chain under the optimal policy that exists diagonal function that satisfy a bounded change for every possible transition. And whenever the state is above the threshold, the value of the diagonal function is above some threshold, the function admits a negative drift. Here, the diagonal function can such diagonal function exist for queuing systems. Here is a very simple example for the two queues example we seen earlier. And I want to emphasize that our algorithm does not need to know the exact diagonal function. So under this assumption, with proper guarantee from the MC oracle, our algorithm outputs a sequence of stable policy. So here epsilon corresponding to the Q function approximation and tau corresponding to the temperature for the softmax, and the minus alpha is the negative drift for the diagonal function. So basically, as long as the epsilon and the temperature that's small enough, then we can ensure that the policy is stable. And moreover, the sample complexity per time steps is finite. In particular, it scales through the drift parameter as follows. I do mention that our algorithm does not depend on the exact diagonal function, but you can tell from the results here, the parameter, in order to ensure the stability, the parameter in some sense depends on the drift parameter, which is unknown. So we also developed an adaptive version of the algorithm that can try to find the proper parameter automatically. And the key idea is to use statistical hypothesis testing. And we can also improve the sample complexity from super polynomial dependence on the drift parameter to polynomial. I'm happy to discuss more offline about this part. I'm running out of time, so let me skip the last part about from stability to optimality here. Okay, before I end my talk, I just want to share some of my thoughts on reinforcement learning methods in general. Some empirical work indeed shows promising and exciting performance of RL-based method for challenging queuing networks. For example, consider switch scheduling, which is a very difficult problem. We try Monte Carlo Tree Search with function approximation. The performance is given by the blue line here. We can see it's outperformed the well-known max waste matching and achieves comparable performance of the best known policy, max waste alpha match policy. So I do believe that reinforcement learning has the potential of finding a better policy and will serve as a performance benchmark. I believe the reinforcement learning also has the potential for other applications. With Sean, Christina, and Sid, and some other students, we are currently developing a toolkit of reinforcement learning algorithm targeting for operation research applications. You can think of as an OR version of the OpenAI gene. But instead of robotic control, we aim to provide a benchmark for operation research domain for problems such as ride sharing, ambulance routing, and revenue management, and etc. And to make reinforcement learning practical for application in computing systems, we recently aim to develop the new tools that's at the interface of reinforcement learning theory and hardware design. There are two complementary directions here. One is to design reinforcement learning algorithms that's taking the hardware constraint into account, such as limited memory, power consumptions, and maybe latency requirements. And secondary is to design hardware accelerators to improve the most critical parts of reinforcement learning algorithms. For instance, design hardware accelerators for parallel to MCTS. And let me wrap up with a brief overview of my research agenda. My work has been primarily motivated by applications in computer and network systems. I'm also interested in other application domains, particularly operation research applications. I have primarily taken a model-driven approach for stochastic system, focusing on performance modeling and analysis. And I will continue to work on important problems in this area. My work on reinforcement learning focused on the general methodology and with the goal of building theoretical foundation for applications. My recent work explored reinforcement learning-based approach for stochastic systems. And in addition to the results I talked about today, I'm also working on more sophisticated approach using policy optimization and weight function approximation, and also how we can explore the structure of the system to facilitate the efficient learning. And a long-term goal of my research is to bridge model-based and the data-driven approach. For example, stochastic model can be used to guide the designs of reinforcement learning algorithm, such as the choice of function approximation architecture. And in the other way, we can utilize reinforcement learning to provide insights for designing simpler and robust algorithms. And there are many challenges here we need to tackle before we can make such data-driven approach more practical and insightful. But I think there are many exciting problems here I would like to work on in the future. That's all I want to talk about here today. Thank you all for your attention, and I'm happy to take questions.
Oh, can't see me. Thank you, Qiaomin. We have a few minutes for questions, maybe a couple of questions. Open the floor up, if you will.
So, Qiaomin, I have a question. Oh, sorry about that. Is that Shane?
No, go ahead, Jim. No, you go.
Okay, I have a question about this last part of the stable policy. You have slides this alpha, the Lyapunov function drift.
Yes.
I think it's a very, very nice result that you don't really need. Next slide, the one that have the results there. Yes. So is this something that results something? Okay, so your result, good. So you don't need to know the exact form Lyapunov function. You just need to know the drift, right? The alpha represents the drift, right?
Yes. Yeah, exactly.
That's very nice. I think that a lot system that stochastic network, that alpha represents should be proportional to the
gap of the load.
Excess resource, right? Excess resource. So depending system resource minus load, that's the alpha. But you don't know exact alpha, there's some constant, but you know that the system scale, when something. So, right, so this is something, in your here, this theorem, you need to know exact this load gap.
Yeah,
right?
for these particular results, we do need to know. But as I mentioned, so we have an adaptive version of the algorithm. So that can automatically try to find a proper parameter for the epsilon and tau here. So we don't really need to know the drift parameter. And instead, we can try to identify the parameter adaptively by tracking the system state.
Okay, this is very, very nice. I think this is the first kind of result I have seen. Yeah, something for potentially such a difficult, intractable problem, you have some kind of this kind of bounds. So it motivated me to try to learn more about this. This is nice. Thank you.
So yeah, maybe, sorry, Sasha, I'll just quickly ask my question if I may. Actually, I have a few, but we're talking later, so that's no problem. Maybe one thing I'm curious about is that many of these problems either have massive state space or infinite state space. And when one focuses on Q factors, one is very focused on sort of state action pairs and estimating those. How do you extend your main ideas to the unbounded state space situation?
So that's an excellent question. So first, for unbounded state space, you can think about two main approaches. So of course, the one is using function approximation. So you can use a more sophisticated function approximation to deal with the unbounded state space, either linear or maybe more general. And you can even use the neural network approximation. So this is one. The second approach here is, I think for here, I mainly focused on queuing system. Actually, queuing system has a very nice structure. So here, the nice structure, I mean, whenever your system is stable, you can imagine the system kind of concentrates, or most of the time, will fall in a compact, a smaller finite state space. And whenever you are coming out of this finite subset, you can use our idea of kind of like using Monte Carlo Tree Search or some other more locally approach.
So you would concentrate your observations around that compact set, and then when you're outside that, you use some stabilizing policy to get back into it?
Yes, exactly. So you can imagine with this stable policy, it will gradually drag the system back to the finite subspace.
Thank you.
Other questions?
Yeah. I'm interested.
Sasha, go ahead.
Yeah, I'm interested in financial engineering applications to reinforcement learning. So, for example, the option, I would imagine that an American option pricing problem could be related to this. So I'm wondering whether you have some comments about, the role of, of noise essentially in modeling a Brownian motion or essentially how different is the setting of, let's say, pricing an American option to playing a strategic game like Go? And do you think reinforcement learning will work in both cases or is more adapted for strategic games?
Actually, whenever that's an excellent question. First, whenever it involves the multi-agents, it becomes way more complicated. So we recently also started the setting with only two agents, and then the algorithm design and analysis becomes way more challenging and difficult compared to the single agents, and left alone the multi-agents. But when it comes to the financial applications, indeed recently there has been quite some work using reinforcement learning for the multi-agents setting. Actually, I have been discussing with Christina on this type of application as well. There are many interesting problems here. And I think currently the most results we have seen kind of like try and error. They try different reinforcement learning algorithm and see how it works. So that so far there's not so much systematic approach for these type of applications.
Okay, thank you.
Yeah.
Okay, folks. Thank you, Qiaomin, for your excellent talk. We really appreciate it. Let's thank the speaker again if we can. Thank you all.